Our global demand for electricity is surging to levels we've never seen before. Between the explosive expansion of artificial intelligence, countless new data centers, and the growing strain of climate extremes, our grid is struggling to keep up. The solution to this crisis requires a combination of features we've yet to achieve in a single source: a reliable baseload power supply that produces zero carbon emissions, cannot melt down, and runs on fuel extracted directly from seawater. Today's nuclear power relies on fission, taking heavy, unstable atoms like uranium and splitting them apart, a process that leaves behind radioactive waste. But there is an opposite reaction. Fusion takes the lightest atoms in the universe, like hydrogen, and forces them together. Mastering this shift from splitting heavy elements to combining light ones provides a path to a power source that is clean and practically inexhaustible. There is a physical barrier standing in the way, called the Coulomb barrier. Because atomic nuclei are positively charged, they fiercely repel each other when they get too close. Overcoming that fierce repulsion naturally requires an incomprehensible amount of crushing gravitational pressure. It is the exact process that powers the sun and every other star in the universe. Since we cannot replicate the gravity of a star in a laboratory, we have to substitute pressure with extreme heat. We must heat hydrogen gas into a charged state called plasma, pushing temperatures beyond 100 million degrees Celsius. This presents a central engineering paradox. How do you hold a 100 million degree cloud of plasma without vaporizing the physical machine you built to contain it? The primary answer is a device called a Tokamak. It is a massive donut-shaped machine designed to act as an invisible, heat-proof cage. This cross-section shows the mechanics. Superconducting magnets surround the vacuum chamber, generating a powerful magnetic field that floats the superheated plasma in the center. Because of this levitation, the 100 million degree core is suspended in a vacuum, never touching the hardware walls. Building a levitating cage of this magnitude is a significant hardware achievement. But keeping the plasma suspended is only the first step. The real difficulty is controlling the chaotic fluid trapped inside. To achieve fusion, we must maintain a precise balance of temperature, density, and confinement time, a metric known as the triple product. Plasma is a fluid, and under these extreme conditions, it tends to writhe and rebel. The glowing ring can rapidly warp and bubble, succumbing to violent disruptions that threaten to stop the reaction instantly. These events, known as tearing instabilities, happen in fractions of a millisecond. Human reaction times cannot detect or correct them. We are now deploying artificial intelligence models to predict these disruptions before they occur, mapping out safe zones within the reactor's operating parameters. The AI calculates the exact required corrections and adjusts the magnetic fields in real time, suppressing those tearing instabilities to maintain the plasma's equilibrium. Artificial intelligence provides the high-speed oversight that makes sustained plasma containment physically possible. Once the plasma is stabilized, we have to look at what is actually burning inside the furnace. The reaction requires a specific subatomic fuel mix, deuterium and tritium. Deuterium is abundant and easily extracted from seawater. Tritium, however, is incredibly rare. To sustain the reaction, the machine must breed its own tritium by exposing a lithium blanket inside the reactor to the fusion process. This fuel mix creates a difficult byproduct. The reaction unleashes a continuous bombardment of high-energy neutrons, which strike the physical walls of the reactor and degrade the structural materials over time. AI is being used here to simulate and discover novel, damage-resistant materials capable of surviving this continuous subatomic bombardment. Building this subatomic furnace requires breakthroughs in fluid dynamics, supercomputing, and material science to operate as a single coordinated system. Progress in this field is measured by two milestones. The first is scientific break-even, the point where the energy released by the fusion reaction exceeds the energy injected to start it. At the National Ignition Facility, scientists recently crossed this threshold. By firing highly calibrated lasers into a target chamber, they proved net positive fusion is possible. The final and more difficult hurdle is engineering break-even. This is the point where the entire facility produces enough excess power to continuously feed the commercial grid. Bridging the gap between scientific proof in a laboratory and engineering reality on the grid is the final stage of the global fusion race. For decades, scientists have faced the joke that commercial fusion energy is perpetually 30 years away. This data shows how that timeline is compressing. The convergence of AI control models, stronger high-temperature superconducting tapes, and heavily funded startups is allowing engineers to shrink the size of these machines, pushing realistic target dates into the 2030s. The stakes of this timeline are immense. If these compact reactors succeed, we can finally decouple our economic growth from the finite resources of the planet. By mastering the subatomic realm and harnessing a star's power on Earth, we provide a foundation for global development that no longer relies on the depletion of our environment.